Okay, so here we're going to take a look at some vector space properties. So we took a look at in the previous that notion of the crazy vector space, right? So as long as so we define addition between two vectors and then scalar multiplication, and those 10 axioms hold, then it is a vector space, and those properties of the vector space hold across all different vector spaces, right? Now, what we're going to do here is we're going to take a look at some theorems about vector space. Now, these theorems they derive just strictly from the axioms, right? So no other definitions or other theorems that will come into play. We're only going to prove these theorems from the axioms, right? So the first one is this theorem that we call, and we've seen previously when talking about column vectors. So the theorem is that the theorem is ZVU, and that's the zero vector is unique. Is unique. Okay. All right. Now, when we have this idea, this type of proof that is asking us to prove that something is unique, right? One approach is to let there be two, right? So for our proof, we'll let there be two zero vectors. We'll call them 0, 1, not plus, sorry, and vector 0, 2, and those come from my vector space V. All right. So we assume they are unique, and from there, we show that, well, they are actually one and the same. There can't be two of them. They are equal to each other. All right, so it's a common technique here when across any kind of when we're being asked to show that something is unique, a common approach is to let there be two of them, right? In this case, two zero vectors, right? And V is a general vector space, right? So again, I want to emphasize here that I want to step away from representing these vectors as column vectors like we're used to seeing them in this course or in previous math classes or physics classes, right? So this idea of a vector is strictly saying that these elements come from a vector space. As we saw in an earlier video, that could be a column vector, it could be a sequence, it could be a polynomial, it could be a matrix. Okay, so I just want to emphasize that, right? Because we are not going to use column vectors on our proof here. Okay, so we're strictly using the axioms, and the axioms are very general, so they don't reference any particular type of object like a column vector or a polynomial or anything like that. Okay, so here, and let them be two zero vectors. So we'll start with, so here, two different zero vectors. Okay. All right. Okay, so we start here, 0, 1, and then we use the property, the zero vector property. So 0, 1 plus 0, 2. So this is property Z. Okay, and these properties are the ones that I'm referring to vector space properties that we introduced earlier in this section. Okay, so from here, we use the commutative property. So property C. And then lastly, we'll apply the zero property again. Okay, and then we get at the end that our 0 vector 1 is equal to the 0 vector 2. Okay, now again here, it might seem trivial, but it's good to kind of work through this and just kind of understand in the background here that this applies to any vector space, right? Once you've identified a 0 vector, that's it. There is only one. There is no other one. Okay? All right. Now let's take a look at another property here. So how about here? Let's take a look at theorem. Okay. Theorem ZVSM. All right, so this theorem has to do with scalar multiplication and the zero vector. Zero vector and scalar multiplication. Okay. All right. So in this case here we have, so this theorem states that suppose that V is a vector space. So V is a vector space, then alpha times the zero vector is equal to the zero vector for any alpha element of the real numbers. Okay, and again, right, all we're using here are the axioms of vector spaces. Okay, so we'll start again here with alpha 0 and applying the property here. I'll apply the zero vector property. Okay, so again, this is property Z. And then from here, I'm going to use for the zero vector, here I'm going to use the additive inverse property. That says negative alpha times the zero vector plus alpha 0, right? So the additive inverse tells me that is equal to the zero vector. And then we have alpha 0. Okay. All right, and again, this is property AI. I'll skip writing property over and over. I'll just write the abbreviation of the property, AI being additive inverse. And then from here, I'm going to associate these vectors in a different way, which again, properties of vector spaces. That's the association of addition. All right, that's what that AA stands for here. Okay, and then now I'll focus here on this second term here, these two terms here, and I'm going to apply the distributive property of vector addition. DVA, right? The distributive property of vector addition. All right, so distribution across vector addition. And then from here, I'll apply property Z, the zero vector plus the zero vector. So that's property Z. And then lastly, what we have here is these are additive inverses. So again, that equals to the zero vector. And that is property AI. And now that concludes our proof, right? At the end, we have alpha times the zero vector is indeed simply the zero vector. So the scalar multiplication of the zero vector, right? Regardless of how that zero vector is defined, right? If it's in the vector space, we're working within that vector space, then any alpha times the zero vector gives you back the zero vector. Okay? Okay. Now, in our book, it works through other theorems which are worth taking a look at. All right, so here, some theorems that strictly work on vector space properties are the theorem AIU, another one of these uniqueness theorems, right? ZSSM, AISM. Lots of good examples here, how to approach a problem, how to derive proofs or write proofs using, right, strictly the vector space properties. Okay. All right. So it'd be worth your time to just kind of go through them and on your own time try to see if you can work through those. Now, another thing as we move forward here is that some of the definitions that we've talked about before, we can recycle them and use them in the context of vector spaces and not just column vectors, right? And mainly what I'm referring to, a big one, is this idea of a linear combination, right? So, for example, if we have this statement, this expression 5u plus 7u2 minus 13u3. So we have here a linear combination of the vectors u1, u2, and u3. Right now, we talk to them in reference to column vectors, but here there's nothing that, there's no mention of a column vector. They're really just vectors that come from a vector space. And within that vector space, right, we know that since it's a vector space, scalar multiplication and vector addition is properly defined. So this type of statement, this linear combination, can be recycled and thought of, well, if it's a polynomial, I know how to do this. If it's a matrix, I know how to do this, right? This definition spans across any vector space, right? Not just column vectors, right? That's the abstraction here that we are trying to get at, right? It's unambiguous, right? These vectors are just vectors from a vector space, and those operations are properly defined. So whatever space I'm in, I can apply it to have a linear combination of those vectors, whatever they may be.